Okay, hi. Yeah. Test. I have a voice. I'm actually testing it too. By looking at the view meter anyway. So I'm thinking, shall I do this in 3 dimensions with an idea of higher dimensions, or just do it for the case that we need? And I think I should do the latter, because this drawing thing is 2-dimensional. And really I only need it at the moment anyway for 2 dimensions. And well, this case, right? So for example, here we have a line which is directional. This one points down. These are negative values, and here we have positive values. So the direction is from the top to the bottom. And I want to calculate, find the intersections of that line with the rectangle that is the outside of the window. So we find 2 points, this point and that point. And I want to know if I can write the algorithm in a way such that this point is added first and that point. Why this point first? Because this is the point on the negative side. However, if whatever I have defined as my line points the other way, so if this whole thing is rotated 180 degrees, then I want to add that point first. Now this line is defined by its normal. And well, the normal that you get by rotating from the y-axis to the x-axis, positive y-axis to the positive x-axis. The long side here is the x-axis of this rectangle. So this is the positive side, positive x-axis here. Then this must be the y-axis, and this is the positive y-axis. Therefore, the rotation goes from positive y-axis to the positive x-axis. And well, if you talk about 90-degree rotation, then we mean that way. From positive y to positive x, and that is the direction that we will rotate in. I think the direction of the line, so a unit vector that points in the positive direction of the line. So that would be this point here, 1, or origin here, end point there. That rotate that 90 degrees, and then we could come here. Then this is the normal vector for this line. Now, God, it's the music again. Okay, the normal vector of this line. So we start with the unit vector of the x-axis, and we rotate it also counterclockwise. So in this case we would rotate from the positive x-axis towards the negative y-axis. But it doesn't matter, it's just the same direction. Just with the inverted y-axis, because the y-axis is inverted, normally you would have I can draw like this. Yep. Nope, that's selection still. Draw. So normally, of course, you have a y-axis like this and an x-axis like this. That's how you normally draw in mathematics. And then now I'm starting to I'm starting to doubt myself now. What is the normal? I would say the normal here is pointing up, actually. Oh, yeah, no, okay. No, that is actually correct, yeah. I was going from the... No, it's not correct. So that means that we would have to rotate the other way. Well, that is kind of important. Now, let's look at the code. So the point is that if you have a line, in this case, let's say the x-axis, and we have a direction, then the line is defined by a unit vector anywhere, length 1. 90 degrees here. 90 degrees being that is normal to this line. But now, is it this way or is it pointing that way, our normal vector? That is the first question that you have to ask. Line extent, that's not where I wanted to look. No, it should be in here. Coordinate system. No. There's the normal. So I take the x-axis as an example, then axis is 0, because this cons expression is 0. And then we get a vector with an x and a y coordinate, where x equals 1 and y equals 0. Yeah, so that would be what the hell? Just wall. What is this? Well, I don't know what it is, but no. What? That's what I want. Okay. Yeah, so this is the origin, and then let's say we have 1 is here, and then this is 2, and here's 3. So this defines the direction into the positive x-axis, and this point here is x is 1 and y is 0. These are the x and the y coordinate of my direction vector, because a direction is just a unit vector that points in that direction. So the CS axis direction y equals 0, and the CS action direction x equals 1 for the x-axis. Therefore, the normal will become, the x coordinate of my normal will become -1. And the y coordinate of the normal is going to be 0. I'm saying that wrong, am I not? Y was 0. So the y coordinate will become +1. Okay. So the normal is this one. +1. And then that's the y coordinate, and the x coordinate is 0. Well, I moved the origin of this one here, so it just means it's vertical. Do I have an eraser or not? Can select. Cancel. Okay. No. What is this thing doing? I just want to delete it. Select another way to select. That's better. Delete. Yes, so we rotate actually in the normal mathematical graph where the y-axis points up. We rotate the direction 90 degrees counterclockwise to get the normal. That is, the normal has an x-coordinate of 0 and the y-coordinate of the normal becomes equal to the x-coordinate of the direction vector. The y-coordinate becomes equal to the x-direction. Yes, okay. But in our case, the y-coordinate is pointing down. So actually, we have it mirrored. This is the positive y direction. Which means that the 1 here is actually there. This is -1. And thus, our normal looks like this. It still points in the positive x direction. But because our y-axis is mirrored in the horizontal x-axis line, and that's not what I wanted. Also not what I want. Having a hard time deleting stuff, it seems. Gets better and better. Okay, so this here is the normal. Let's call this n. And I just shifted the origin, right? I mean, otherwise I have to draw. I should draw it here, I guess. The normal of the x-axis. Most importantly, let's just work with the y-axis always pointing down. Then it corresponds to the thing that we draw. And so we rotate the direction vector clockwise, like that. 90 degrees. To get a normal. And of course, counterclockwise to go from the normal to the line direction. Now the more general case then is we have a rectangle, which is our window. Defined by 4 points. 4 corners. And an arbitrary line. Now let's draw a line through this. You're going to draw it like this, or this, or well, this. Well, let's choose the same thing as I have in my... Oh, wait a minute. I still have to rotate a little bit. Huh? Oh, it's not rotating. Gotta be kidding me. Rotate. Okay, just a little bit rotated. This is enough. It's not the same as we had in the beginning. Then I had rotated it more. Let's rotate it more. Let's go like this, I guess. Okay, I'll just put it like this. Is it not the same? No, also not the same. But I'm gonna go with this, and though this is positive, and this is the x-axis. Okay, and we want to talk about the x-axis. So the line goes from this side to the top. In this example. So this is our line. We're going to find this intersection and this intersection. And the x-axis, the direction is obviously in that direction. Directional line. Positive direction is in that direction. Which means that our normal, because this also has a mirrored y-axis still, despite the rotation. It started like that and we just rotated it. The green one is easier to see. This is the positive x direction. And here you see the y-axis, but it is negative. The y-axis, positive y-axis pointing down here. Same thing here, x here, y is up. So we have to rotate clockwise 90 degrees to get the normal. So, okay, that is the direction. So our normal points in that direction. This is the normal, 90 degrees. Normal. And now we run over all pairs of corners. For example, this corner and that corner. And then we calculate the distance of that corner to our line in normal vectors. So obviously this one, well, the distance is the perpendicular distance. Again, 90 degrees. And the numerical value is then in number of normal vectors. So this is about 1 to 2.2, say. So this distance is plus 2.2 because it is on the side that the normal points to. Well, this one is going to be like minus 0.8. Minus 0.8 because it's on the opposite side. The only thing that really matters is that this is plus and this is minus. So this point is on this side of the line and that point is on this side of the line. Therefore there must be an intersection point. And therefore we calculate it and then we find it. And then the question is, which do we find first? This one or this one? Well, that depends on how we run over the corners. And we run over the corners by running over one corner in numerical order and then finding connected corners in some way. So that really matters, doesn't it? So yeah, we begin with finding out and then enumerating the corners. I have to look at the code for that, I'm afraid. This is the behavior block. the corners are put in an array, and I'm talking about the index. So I want to find the index of this array for each of the corners. That should be filled in the constructor, which is here. I see I didn't know how to write adjacent back in the day. No, just I don't know when I wrote this 2 years ago. Because now I'm starting to doubt myself again. Nah, it's with an A, come on. Adjacent, yeah. Adjacent corner vectors. I'm hesitating because adjacent means next to each other. I would say that means they are connected, which is obviously not enough to create a hyperblock. You can only draw a line then, single line. So I think it actually meant here like opposite, diagonally opposite. So you have just one corner, and then the other corner must be the corner where every coordinate changed. So I'm gonna make this opposite. Yeah, so in the case of the hyperblock, you can define the whole hyperblock with just 2 points, because you just every dimension has a side. So by adding the length of the respective side to each of the coordinates, you get the opposite point, and then you have all the sides. I'm defining a base here as C2 minus C1. Okay, so let's draw this. Well, it's very arbitrary. You can just pass whatever you want. So let's draw this for the case that we have at the moment, as in, how do I construct my hyperblock at the moment? Pretty confused again here, because I've been working on this. So I think I'm in an... I still have an open editor. No, I don't. Where did my code go then? What? Yesterday we during 3 hours stream I worked on this intersect function. Which I put above display. It's just gone. Oh, wait a minute, I remember. I test my changes. Let this be empty. It's not empty. I removed that. That's probably not a problem. Git stash pop, I think, should do the trick. Yeah. So you don't know, it should be empty. Yeah. Okay, the new function intersect is doing this, but we're passing the hyperblock to it. Therefore, this is the hyperblock, and as you see, indeed, these are just two opposite corners. And I use the origin. Well, that this is the window, so the top left of the window is C1, and then the opposite side is C2. So we can now draw that in here. I mean, C1 is the origin, yeah? To the top left. So this is C1, and this is C2. That's how the window is being passed. Which in turn means that my base is C2 minus C1. So I'm going to use a different color, I think. Colors, no colors. How the hell do you change the color here? Pencil. Oh, no. Not really seeing it. Choose brush. You can pick an eraser. It's a bit fuzzy brush. Big fuzzy brush. Okay, this can be deleted. I want to delete something. Don't have a brush or nothing. What do you think? I still didn't figure out how to change the color. Well then, no color change. I suppose. To go back to the pencil. And then I'm just going to draw my base, which runs from here to there. This thing is called base. Note that in terms of the window, this is X and this is Y. And I think I enumerate those as 0 and 1 because this base is stored as an vector type, where the vector type comes from the current file. So I think it's defined on the top. So this is two float types, which we have defined as a double. And I would be extremely surprised if the 0 wasn't x. Let's even just assume that without checking it. We already see that. So if this is that array and we pass, I pass it as initializer list, passing the window width first, and then the window height. So yeah, 0 is the x direction. Now we just run over all the corners in whatever index they have. And we run over all dimensions, yeah. And the D is then used as index into base. And well, n is 2, so we run over the x first. X is means the 0 means x, and then we do d equals 1, which means the y. Bit then changes from 1 shifted 0 the first time, and then shifted 1 the second time. So bit is first 1 and then it's 2. And we do a bitwise with the CI, meaning that the least significant bit corresponds to X and the most significant bit corresponds to Y. And then we add base if the bit is set. Okay. So that means that not adding base at all means that all bits are 0. So this is index 0. And if we just add the x coordinate of base, then the least significant bit was set. So this is well, 0, 1. And if both are added, that would be 1, 1 binary. Call this 0, 0 then. And here we have 1, 0. So the corners are numbered 0, 1, 2, and 3. Which is absolutely nothing to do with the direction. Now I do want to find this one first, which coincidentally happens, because I bet we start with 0 and then we look for all connected corners, and I bet we first find 0, 1 and then we add that one, and then immediately after that we find this one and add that one. And we will not consider this one because that's well, from 0, 0 to 1, 1. That would be flipping 2 bits, which we don't do. We only flip 1 bit, so we get all the connected corners. So here the calculation happens to determining the intersection points. Hi, Amon. Here we do determine something related to the direction of our line. Namely, each corner here is marked by index, on which side of the hyperplane they're on. Apparently this boolean here is set to true if the distance is negative. I thought the comment literally says somewhere that it is in terms of the normal vector, so distance, return the number of normal vectors that have to be added to P to end up on this hyperplane. Oh, this is the other way around. The sign tells you which side of the hyperplane the point is on. Well, if this is correct, then we go from P towards the hyperplane, meaning that a negative value means, well, let's say a positive value, easier to think about. A positive value means that it is on this side then, because let's say this point here, in order to get on the line we need to add n, a positive number of times, going in the same direction as n, and then you reach it. And then if you are here you have to subtract n, so that would give a negative sign, negative distance. So this here is the negative distance. And this side is the positive distance. But only because the normal is pointing that direction, which is only the case because our line is pointed in, well, to the left, to the bottom left. I do want to check it if at all possible though. If this is correct. I guess this is a dot product. Yeah, well, not trivial. I don't see it. I'm just gonna believe it is. If it's not true, then we'll probably find out because it just doesn't work. So I'm gonna believe that this is indeed going from P to the hyperplane, to the line. And then if the boolean is set to true, if that is negative, then that means that it is set to true for the side that the normal points to. That was the negative side. That means that we are on the side that the normal is pointing to. So this one is marked as true. Seriously. It's doing the weird thing again. True. See, that suddenly selects stuff. Stop selecting stuff. Paint into a layer. Penalty. I have to turn that on or what? This one's marked as true, and all the others are false because they are on the other side. Next, we are running over all corners in the direction 0, 1, 2, 3, thus. And then toggling bits in the direction again X first. Meaning that we first flip the X, go to the other side by flipping the X side, and then we flip just the Y side. And then I compare the boolean just to see that they are on opposite sides, and if so, then we add a new intersection. So in this particular case, we would do 0 and then flip X, and this is the first one that we find. So this one is added first, and then we still use this one and we flip the Y coordinate. Then this is the second that we find. However, that's one thing. Then we go to corner number 1, flip again the x-axis, and I would say then we have this one and this one, but then in different order. That's still on the opposite side, so then we add this one, and then I flip this one, but there's on the same side, and then we go to this corner and we flip the X, but that's on the same side, and then we flip Y, and that's again on the other side, so then we add this one. Well, that's wrong. We should only add each intersection point once. In this case, it wouldn't really matter, I would say. Well, you could say, let's say, if I insisted on this one adding first, then we could go for the 2 and the 3. That would be the only option. But then somehow I would have to reject this one, but add 2. And then not reject the 3. And then reject the 4 again. Okay, now we have, that was just dumb summing up what is happening. Now you have to be smart to find out the more general case, because this is just one case. How can we now make sure that we add this one first? Also, if the line is pointing in the other way, or it's cutting here or there or anywhere. Many different cases. Let me think. independent of the line. This is my window. We first consider this point flipping x. So we first consider this line. Then we consider this line. At this point the flipping y. Then we go to that point, which basically also means flipping x. So this is 0, 0, we flip x, we go here. And then we consider flipping x again as first thing, which is kind of weird. So consider this one again. Let's give it a little arrow. One, having that one and then using that one, and this is going that way. This one is then going the opposite way. And then we get this one. By first flipping x and then y. Then we take this one and we flip x first, and then we flip y. That was from here, and then we go here, we flip x first, so this is 7, and then this is 8. That is how we search the rectangle, provided that this is C1 and this is C2. My first intuition is that we can just simply stop after, well, let's say 1, 2. We cannot. How can I get rid of the duplicates to begin with? Yeah. Well, only considering larger values. So let's say we also have to always point towards the larger value. Then you get automatically the larger corner index, that is. So this was corner index 0, 1, 2, and 3. So one way to get rid of the duplicates is by not considering this one, because it points from a higher value to a lower value. So you remove that one, and here we remove this one. And remove this one, and we remove this one. Which then effectively turns this into 3 and this into 4, but well. So we would add this one, then this one, then this one, and then this one. Well, consider anyway. And then we add them or we don't add them. So there is no way, I mean, with the current code, we add them or we don't add them. So if there is an intersection point for number 1 here, let's say there, that would be always added first. Because it has to be added. So at the moment I consider 0 and 1, I see that it's on the opposite of the line, and then we immediately add this. But I want to add a negative thing first. So what if my line points in the other direction? So I still have like, let's say I could have a line like this, or a line like this, or a line like this, having the other intersection points there, or there. And then depending on the normal, I want to not add it if it is the positive one. So let's say these lines are all pointing up. Which means their respective normals are pointing that way. Then I don't want to add it. And if the normals are flipped, then I do want to add it as first thing anyway. Well, flipping normals means that every corner is suddenly on the other side of the line. So I could express this as the sine, something that expressed in the sine of the distance of a point to the line. Which means that we are looking for a point that is a corner that is on the same side of all these lines, which is only this one. Or not. Yeah. Point 0 here is on the positive distance, so you have to travel from 0, corner 0, a positive number of times the normal to reach the line. So this direction is the same direction as that, or this direction is the same direction of that, or this direction, which is the same direction of that. So this one has a positive distance, and that one is on the other side of all lines, otherwise it would not cross here. So this one has a negative direction. And that then is why we don't want to add it, at least not first. And then if we reach the 3 here, let's say I reject the 1 because we don't have our first point yet. So 1 points this way, and for the first point to be added, I want the current point, so the outer loop corner, to have a negative distance. Yep, so first an S here. The first intersection, why are the words so long? Point negative distance for first corner. It's the outer loop, say. which means the boolean is set to true. So the side, the same side is true. For first corner. I can implement this. Not sure yet, but it looks like it. And I don't think I used anything that now it depends on the order really of the corners, corner indexes. So this should work for any orientation and any line then. Or does it? I have the feeling I am making use of some dirty coincidence here. But I also have the feeling that this might work. Annoying thing is that I can now implement this, but then we have to do all kinds of tests to make sure that it works. Yeah, why not? But before I do that, I want to verify that this indeed returns 4 intersections, which it seems to be doing, which would be totally a bug. Okay, I picked the first two. But it definitely should then assert, you can add an assert here that this intersections thing, and that is a vector, isn't it? Yep. I doesn't seem to make any sense to have a size other than 2, but I think it's going to be 4, so this assert should probably fire. Oh, I never tested this at all. Yeah, okay, so the order was not determined yet, but we're working on that. So I want the first one to be from. In the end, then this should work. Matching function to intersect. Candidate template ignored, couldn't invert template arguments, yes. Yeah, we can't. Now match a constructor for initialization of standard tuple. Kotaro is right. Well, maybe I'm wrong anyway. Let's try Kotaro's attempt. No, Kotaro is not right. Still the same error. Matching constructor, initialization function, template specialization. Casted here in instantiation of member function, blah blah blah. Code candidate constructor template not viable, cannot initialize list argument. Standard const array. Yeah, well, I'm still gonna say he's right if it actually should have been 2 braces. Also not. No match constructor initialization of tuple. Initialization function template specialization requested here. Requested here. Cannot convert initializer list argument to const standard array. Can the template ignored? Couldn't infer template argument allocate? Okay, let's try this for a second. That works. And then let's use that here as well for a second. At least now it compiles, and then we run the thing. Assert. It's not asserting. How is that possible? Well, let's first try to fix this. Cannot infer standard make tuple. Seems a bit weird that you have to tell it what the type is. I mean, it doesn't. I'm returning that. Like that. So now we have way more directly telling it that this is an int and that this is now trying to initialize a standard array. .cs2. That's the array. I'm missing a And this is definitely the correct way to initialize an array. So I don't want to hear any word about tuple anymore. New matching function for a call to make tuple. Where it does exist. Elements. Candidate function template not viable. Cannot convert initialize list argument to standard array. And why is that? Okay, one brace down. The gamble game. Still nothing. Instead, let's. They're still talking about infer, right? So, okay. There you go. Now you know what it is. I think array always needs two braces, so we'll try that one first. No viable conversion from math point to .cs pixels. Yeah, this is not a temporary. Oh, that's why it has been failing all this time. Yeah, okay. So I allowed to return .cs, so we have like the return type is .cs. Then we can do return and then a math point, because then the math point here is a temporary, which then, and that the .cs can be constructed from that, because it takes an R value. But this way, apparently, it's not an R value. Well, apparently, it's just not an R value. It's this. So we kind of have to turn this from CS into an R value. Which you can only do by constructing it in place here, instead of putting it on the stack first. Or I would have to type standard move here, but that's too dirty, and I have a comment with that constructor that explicitly forbids the user to use standard move. I don't know. I would say unless you know what you're doing, but okay. So let's try to fix this between big quotes by not using from CS, but constructing it. In place here, so now it's a temporary. At which point I have to say it becomes a bit nonsensical anyway to use a math point, because if I can construct a math point, I can also construct a point CS the same way. But by now I just want to see that this compiles. Yes. And then we want to see if now I can delete this cast here. Well, cast. I'm not going to tell it anymore that it is an array. It should know that if I call make tuple. That still works. And then the question is, well, that one worked. And do we even I have to. Let's try to delete one brace. By the way, that's. I hope that fails. Yeah, that also compiles. Yeah, well. Okay, one brace down. But yeah, I would say why do I need? I think you need make tuple if it can't infer the type. But why would it not be able to do that? You return that type. So I think that maybe we don't even need a standard make tuple here. We just tell us exactly what the types are. And then return and initialize a list for the tuple that we return. See, all that was not a problem. The problem was just that we need to pass temporaries. Now, if I remove the math point as well, it becomes more interesting. Then I might need to make tuple. I mean, first of all, if I remove it and replace it with the actual type, namely the point.cs, I think that the point template just inherits all the constructors from the base class math point. So this should be exactly the same. And if I delete it completely, then I bet it doesn't know anymore that this has to be a point.cs. Although you could argue, well, the first brace means we're going to pass to the tuple. The 2 is then the int. Therefore, this brace must match standard array. Therefore, the second brace must be something that we want to use to initialize a point.cs. It's all there, in my humble opinion. Let's see, I have that. Okay, now it's complaining about it cannot convert initializer list argument to const array. So it does know that it is an array of CS pixels. And the problem it has is with the whole thing, including the 2. What? That doesn't make any sense. Nah, whatever. Let's just stop here. Okay, I'm still highly confused now why this assert isn't asserting. Why would this function here not return 4 things? So let's just run this in the debugger. Let's see how often we exactly get there. This is just, well, detail, intersect. I'll add a detail. Intersect. And then I think we can write everything to the debug output. I mean, that is the whole idea, right? I'm not sure we can write hyperblocks though. Not sure at all. Is this right? Yeah. Okay, let me check. Can I write a line to an O stream? That would be this line. You can totally not write that. Yeah. What about the base class? Go in the line. Also not. And the math line. The math line at least can be printed. Well, then we only have to add that to print the rest as well. This prints on the point and the direction. Yeah, it's a wrapper. I don't care. Just print the math line here. Just prefix it with the coordinate system. Should be enough. Do I have to include UDLs to string, or is that already included? I don't think it's probably not included. Include UDLs to string.h. Cannot print hyperblock, yeah. Didn't check that one yet, but I had the feeling. I do have an operator OStream. An OStream operator for the vector here. So why not for the hyperblocks? They're even defined like this, as in they work for any OStream, not just the debug output. Yeah, sure. think I was just too lazy to edit, because it feels like a lot of work. Yeah. Yeah, I really wouldn't know how to print this, and why I would even print it if it is not for debug output. I'm gonna add this instead. The whole thing only consists of the corners, right? Look at that. Which means we need to be able to print arrays, and we need to be able to print well, use print on, which means that we need to include utils as print on. Hello Vivek. If you enjoy it, it doesn't hurt to know Python. It's a good language. But if you pause C++ completely, you will not unlearn it, but you will get out of it. So it's gonna be harder. I don't know your memory, but if I stop coding for 1 year, then I have the feeling I did stop for 1 year, not that long ago, 5 years ago, I think. And then I had the feeling I couldn't code anymore. I really have to keep my brain active every day with C++ coding. Well, you're probably much younger anyway, so maybe you can pick it up rather quickly again at some point. I wouldn't, I don't know, if you wait 10 years, then you might as well start completely over with C++. That's the only downside I see. It's not a Vivek, but more Vivek. Vivek. My God, you pronounce the E as an A? Vivek. Is that Russian? I'm learning Russian. Wow. Well, or maybe you just said yes and that I pronounced it correctly. It's Indian. I'm learning Indian. Well, that's as exotic as least. Well, actually, vector doesn't. Arg, maybe I should change this. Oh, it does. There's just a print on here. Yeah, then this is not necessary. It just calls the print on again. For debugging purposes, blah blah blah. Okay. Added all the debug outputs. Need to print arrays. I'm not sure what I need. Either utils, I think, also. Utils debug stream operators. But then again, in each, let's try CWDS first, which might be included from debug.h now I think about it. Invalid operands to binary expression. OStream and standard array. So that was simply not the correct one. Let's try the other one. Okay, yeah, success with your tutorial. And still I can't print an array. Why? Hmm. No, you're just printing nothing. just the AI alert. And the print C escaped. So that's definitely, let's never use that again. Well, except for the AI alert. By the way, included from AI alert if CW debug is defined. Now I think about it. If that's all it defines. Or anyway. This should do it. This prints tuples, standard set, standard map, standard pair. Print a container. Well, an array should be a container, doesn't it? Yup. This one should work. Intersection points. Nothing. It only considers 2 candidates. Yeah, I guess the reason is that we are inside intersection. Sorry, well, inside a namespace. But are we? Yeah, here. We are here, and that's inside the namespace. And inside that namespace, we find a has print on one. And therefore it stops looking. However, oh, wait a minute, we are here as well. Are you now telling me that I have to add the OStream prelude thing here in every print on? Well, only if I need something that is outside the current namespace, I suppose, but seems like a little in array, so I could say using namespace CWDS. No, it's not defined in CWDS. Oh, yeah, I think I start to realize how this works. So this used to work because ADL, argument dependent lookup, would look in standard namespace because C is in standard namespace. But defining anything in standard namespace is undefined behavior. So not that long ago I changed it. I'm no longer defining the OStream operators in standard name in the namespace std in standard namespace. Therefore, it doesn't find it. And what I did is I defined them in my own namespace, and then I include that namespace in the out macro. However, that macro is calling this function, and then we lost that using. So now I have to add that again. So we can use OStream operators that print std stuff if used directly in an dout macro, but not from a print on, which means that if I do something, yeah, in a namespace like this one, I have to add that stupid macro. And I forgot, of course, what it was called, but something with prelude in it. Grab sources x prelude. I guess this one. It's the same as that one. That works, okay. So now it's printing when we enter that function. Let me see. I think I have to turn off Gyro window. This is not very helpful. entering intersect, that happens a few times. Which one is interesting? Because it happens for every axis. So we have two coordinate systems and each has two axes, therefore we call it 4 times. And then this one is the red one, the second one. Although it's not rotated now, so it doesn't really matter. Well, I could even look at this one, just the first one. It's still returning only 2 intersections. So we have axis, the direction, here this is the x-axis. X is 1 and y is 0, dus that points into the direction of the positive x-axis. And here we have an array of 4 points, 0, 0, 600, 0, 0, 450 and 600, 450. Which is indeed in that order, 0, 1, 2 and 3. And I guess this is the origin of the it's a point that the line goes through, which is in this case origin in the center here. Why does it print point in front of that? That's in pixels as well. Here again. Don't even have a point namespace. Let's print a line. Is that a line? What's the first argument? This must be the line. Oh, never mind. It's the name. Yeah, pixels is the coordinate system, and then we get the vector, which exists of a point and a direction. It starts to get confusing. I'm using the same notation for printing a member of a class and printing a class that belongs to a certain coordinate system. So maybe I should change this. Yeah, it's not that confusing yet. I suppose. Just don't have a member pixels. But yeah, I don't know. Okay, so let's just debug this call here. Break. Detail intersects. Run. I think you can use the very first one. Next. So the X action is simply pointing to the right, and the normal should be clockwise. Therefore, that should be 0. And this should be +1. And then we create a line. The normal is now 0, 1. And D is the well, something that you have to add to in terms of normals. So that is the apparently negative y coordinate of the center. This 225, half of 450, the height of my window. And then we call intersection points on the rectangle. So already should have a rectangle. This has a array with top left, top right, bottom right, this one, and I mean the bottom left and the bottom right. Step intersection points. We make a result vector which is currently empty. And we run over all 4 corners. And then we set in which side they are on. So the normal is pointing down, right? And we're going to say yes, we're going to say true if they are on the side of the normal. So this point and this point must be true, and those two must be false. And this is the first one, so this one must be false. Now let's just do all of them. So this is also false, true, and true. False, false, true, true is expected. And then we run again over all corners, and this time we run over all dimensions as well, or n is 2. Therefore bit is first 1. And I'm doing... Actually, I'm not toggling it. I kind of assumed that I would toggle it. Now I see that I'm not. I'm just resetting that bit. Yeah, what? CI is 0. What is the point of this? Well, anyway, this I completely read over it. I assumed that we would just toggle. do an exclusive OR with bit. But it's resetting the bit. So if CI is 0, then CI2 is going to be 0 all the time. Which means obviously that this side is never going to be unequal. So you never add anything actually that connects to this. What? Well, we do once we started with this one. Okay. Yeah. Okay. Well, that solved it. Quit. Let's now implement my idea that I had. So I think that if we only insert the first intersection point if the side is true for the outer loop one. Yeah, that's the. And then I have to use toggling instead of resetting to 0. Otherwise I don't find them in both directions. Yeah, but I don't know who wrote this. Well, it must have been me. Part of my subconscious that is still a genius, because I don't get it. But it might just work. Let's try this. So step 1, we must toggle instead of yeah, problematic is that what I figured out, it works for 2 dimensions. Does it even make sense in 3 dimensions? Yes, it does. No, it doesn't. You always have 2 points. Is that true? Okay, let me think. There are loads of points in that case. Oh, wait a minute. Sorry, this doesn't make any sense. If this is a hyperplane, I'm gonna back. What? Intersection. So you return the intersection of the line through C1 and C2 with this hyperplane. Why would that be a point? Let E be a line through C1 and C2. So E is C1 plus some G times C2 minus C1, where G parameterizes the point on E. Fill that in the line equation to find the intersection. I'm calling it a line even here instead of a hyperplane. So normally I have as an equation for the hyperplane. Is that formula never printed somewhere? Yeah, here. So a normal dot product with x plus d equals 0. Yeah. So if d equals 0, then that just means that x is perpendicular to n. So you get a hyperplane of one dimension less than the space that we are in. So the number of dimension of n and x. And if d is non-zero, then if x points in the same direction as n, and where n is a normal with is a unit vector, so then this gives you the length of x itself. And if that n is 0, then that is well, only 0 if the length of x is d in the direction of n. In other words, the whole hyperplane has then at a distance of d to the origin. D is the distance to the origin, perpendicular to the hyperplane. And my problem is that if n equals 4 or more, then the hyperplane is 2 or more dimensions. No, 3 or more dimensions. No, wait a minute. 1, 2, 3. Yeah, I need 3 dimensions. So n is 4, then yeah, the hyperplane is 1 dimension less, so that would be 3-dimensional then. You have some volume that is entirely perpendicular to the normal at some and it's at some distance from the origin. And then this would calculate the intersection between a line through two points and that volume. Seriously. So we have the equation for the line through this point is this, C1 plus G times C2 minus C1. And we fill that into the equation for the hyperplane. So this is the dot product indeed. No, here, sorry. And dot C1 plus G times C2 minus C1 plus D equals 0. And then you can say, well, for which values of G is this gonna hold? Because for exactly those values of G, that this is true, Hmm. Oh, yeah. Oh, yeah, yeah, yeah. So the trick is, of course, that this line has a component in the n direction. It's not allowed to draw a line that is inside. That would be the same for the two-dimensional case. So if you have a rectangle that is the window, and the axis is on top of the edge, then you have many, many, many points. I mean, it just intersects with every point on the top, and you don't consider that. I'm just considering a line that has a component that is perpendicular to it's the other way around. My x-axis is the hyperplane, and then the line, the top line of the window is the line through two corner points, and it's not allowed that they are parallel and on top of each other. And if it does have a component perpendicular to the hyperplane, then there is only one value of g, where it is exactly inside the hyperplane. So yeah, you do get a single point. It's kind of surprising me actually, but it has to be, because as soon as your g is a little bit different value, you immediately lift out of the hyperplane immediately, because you have this component in the n direction. So this does indeed give me a single point. Yeah, okay. Even for higher dimensions. So this follows n dot c1 plus d plus g times n dot c2 minus c1 is 0. For it follow that g equals minus n dot c1 plus d divided by n dot c2 minus c1. So we calculate c2 minus c1, and then we calculate g as the dot product between that divided by the dot product of that, and then we return the point as function of the, by filling g into the line equation again. Yeah, okay. I was just thinking, if you drop a line through a volume, you get a line segment, which is also nonsense. It's either an infinite long line or a single point, because the hypervolume is infinitely big volume. It's just situated somewhere inside a four-dimensional space. So the only special thing about it is that that there is also a direction that is perpendicular to the volume. And if the line has a component in that direction, then it only appears very shortly inside the volume. It's at a single point. Finally seeing it again. Okay, so where did we came from? Okay, so this is a single point. And what I wanted to do now was I'm still trying to think of a three-dimensional thing now. Say a block and a plane through the block, and then we get points for all the how are they called? All the line segments between every corner pair. I can't find the word. But there are 12 of those, right? So you get up to well, there are 12, but the number of corner pairs are equal to half, I guess. N times n minus 1. That would be only 3. No, wait a minute. It's nonsense. Let me just draw it. Draw. The 3. No, yeah, what am I talking about? Of course, it's yeah, a block has 2 to the power 3 is 8 corner points. And then 3 dimensions, so it is 3 times 8 is 24, and then we got each, well, let's call it a side, a line piece. Or vertical, I don't know how to call it. You can ask an AI, but I don't care, so that would be 12. Yep, there are 12. But if then you have a plane cutting through that block, no way it can hit all 12 sides. Okay, this annoys me like hell. I have to ask an AI. Can't even find words anymore. Oh yeah, an edge. Yeah, we'll call them edge then. So a 3D block has 12 edges. And if you cut through that with a plane, then how many intersections can you get? I think 3 is the minimum. Well, 0 is the minimum, but if you just cut off a little corner, then you have 3. 4 is also easy. Can you get more than 4? I think you can get more than 4. Oh yeah, I see it. Oh yeah, of course. In a minute. So you can cut through here and here, and I think it's 6. Spreadsheet. It's just, it's reasoning. I think there's more knowledge question than. I mean, I don't see an AI being able to visualize this, and it's definitely not using mathematics to calculate it. Poor AI. Yeah, yeah, no, I have to agree with that. I think it's indeed, you can make a rectangle a hexagon. It would still be nice to visualize it, though. So intersection, yeah, let's use a cube indeed. Cube and plane. So here's an example. 1, 2, 3, 4, 5, 6. So it runs from 0, and then of course 1 if you just cut the corner, and you want to ignore that. Those are corner cases. Corner cases. So it is 3 or 4. This is 5. 1, 2, 3, 4, 5, and 6. Yep. It's rather smart. It is slowly move it through, so you can see what happens. Yeah. Well, this one is differently orientated. 3 years ago. I could point to my code, my block hyperplane code. That is totally calculating it. But yeah, the new question now is, because if at all possible, I want to do this. I want to have this working for multiple dimensions. Why not? Is there an order for these 6 points? So I'm currently we're working with not a cube but a rectangle and well, cube block or a square, say, whatever, and not a plane but a line. And if you draw a line through a rectangle, then you have 2 intersection points at most, and then they can be ordered clearly because the line has a direction. But does a plane have a direction? No. What would be the order? What would be a sane order to assign to the 6 places where it cuts through it? There is an order. I can assign some order to the points themselves simply by assigning an order to the edges, and I already have that. We just start at the edge that has the lowest coordinates for all dimensions. And then we have, let's say this is the origin here, and then this is the x-axis, and this is the y-axis, and this is the z. And then we order the axis as first x, then y, and then z. And then this is then say 0, 0, 0. And this is 0, 0, 1, and this is 1, 0, 0, and this is 0, 1, 0. And this is 1, 1, 1, of course. And then if you just order them such that the one of the x is the least significant bit, you have a binary numbers of 3 digits. Sorry, of 3 binary digits. So then they are ordered from 0 to 8. 0 to 7. As in 0, 1, 2, 3. That's not 3. Sorry, 0, 1. This was y, so that is 2. This is 3. This is then 4, 5, 6 and 7. Yeah. But wait a minute, that's the ordering of the corners. I still don't have an ordering for the edges. Okay, let's use the most intelligent AI and use that as a brainstorm thing. I am going to start a new one. I want to establish an ordering for the intersection points of a n-dimensional hyperblock with an n-1 dimensional hyperplane. It is probably sufficient to solve this for n is 3. N is 2 is not sufficient. I also don't think it matters for the algorithm. If the block is a cube. If you scale the n-dimensional space to deform the block into a cube, that should have no influence on this ordering. I propose to order the 2 to the power n corners of a hypercube. Now it's a cube. By enumerating them as binary numbers. Where there is an ordering of the dimensions. There is a given ordering of the dimensions. E.g. for 3 dimensions or for 3 we have the x, y and z directions, and we put those in that order by assigning them respectively 1, 2 and 4. Furthermore, we might as well assume that the cube has a side of one corner is in the origin and one corner is in 1, 1, 1, dot, dot, dot. Then a binary number of n binary digits denotes a corner. And as such, the corners are ordered. Next, we can use this to order the edges. Well, the number of edges are the number of for an n-dimensional hyperplane, hypercube. That's equal to the number of corners of an n-1 dimensional hypercube times two. You make a mirror and then adding the number of corners again. That's times 3. The number of corners gives us sorry, 2 times the number of edges plus the number of corners. So I need a formula for the number of edges and the number of corners. So just note that the number of corners of an n-dimensional hypercube is 2 to the power n for obvious reasons. Is that correct? Yeah, I mean that's exactly that's exactly what I used here. Yeah, you can easily see this by constructing the hypercube. So if you have an n-1 dimensional hypercube and you want to go 1 dimension higher, You just make a copy and you move it perpendicular to all previous dimensions over a distance equal to the length of the edge, and then connect all corners. So you had this number of edges, and then you make a copy. You move that new copy into the new dimension, and then you have the same number of edges in the original plus again the same number of edges in the copy, and then you connect all corners. So that would be giving new edges that are parallel to this new dimension. I don't know if I want to explain that to the AI. I think I'll just give this formula. Yeah, I still have to define then a bottom thing, of course. So C, well, we know C. So for one dimension, the number of corners are, well, that's too difficult. Well, that's 2, right? So, I do that, 2 to the power 1, yeah. So, what do you see? 0 is also 1. 2 to the power 2, 1, no, it's 1. So C0 is 1. 2 to the power 0 is 1. And E0 is, well, it has to be 0. Huh? I mean, what else can it be? Thus, E, because C is trivial, E1 is 2 times 0 plus 2 to the power 0, well, plus C0 is 1, which is correct, because in one dimension the hypercube is just a line piece, so that should be 1. And E2, that is a square, is 2 times E1 plus C1. Now we just calculated E1, that's 1, so that is 2 times 1 is 2. And C1 is 2 to the power 1, is also 2, so that's 4. And E3 is 2 times E2 plus C2. So 2 times 4 plus, you see you had 4 edges in a square, and we make a copy, so now we make a cube. So we had the bottom is the square with 4 edges, and we move it up to when they have a square at the top, which also has 4 edges, and we had 4 corners that all make new edges. And then you get in total 12 edges. Now, how to order those 12 edges? So each edge is comprised of 2 corners. Say A and B. Then we can write denote any edge as A and B, where A is, well, less than B. So this uniquely defines all edges. Provided you take care that A, X, or B only differ in one dimension. They must be adjacent. For example, in 3 dimensions, a cube, each corner each of the 8 corners has 3 adjacent corners. You can toggle each of the 3 bits. Which gives 3 times 8 is 24 pairs, but then we count each edge twice because we also include B, A. And the total number of pairs with total number of ordered pairs, of ordered corner pairs, of ordered adjacent corner pairs, is 24 divided by 2 is 12. So this, now I have an ordering for whatever intersection points would exist. However, I wanted to involve the direction of my line, at least in the 2-dimensional case. And a line can have a direction, but a plane can't. And I really don't see... I mean, a plane doesn't have a direction. It's just... It does have a normal, however. So the normal has a direction, so the plane has a side. And they want to have that side then have an influence on the ordering. I think we can just pick this ordering and then invert the ordering, whatever. If the hyperplane is... if the normal of the hyperplane is inverted. That could be our definition. Okay. So I also want the direction of the normal of our hyper plane to play a role. It seems that the only sensible way to incorporate it is by reversing the order that we just established. If this normal is inverted. My current problem, I guess, is the question if this has any significance. Geometric value, whatever. Maybe I should use value. Eat that. Okay, let's see if this AI has an IQ of 200. Like I said, I'm just rubber ducking here, but it's always nice to actually see what it says then. This would be a good time to go eat, I guess. Although it's probably only going to think 1 minute. Oh, explaining. Yeah, this is why I like DeepSeek better. Yeah, it isn't as arrogant and self-secure about everything. Considering, okay, better wording. Yeah, GTP5, ChatGTP5, yeah, it has the tendency to formulate everything as if it is the world's expert on the topic, even if it has no clue. But maybe it will impress me. Short answer first. In 3D, your plane cube intersection is a convex polygon. The plane's normal gives that polygon an orientation. So there is a canonical cyclic order of the intersection points, clockwise versus counterclockwise. I am impressed already. Flipping the normal flips a cyclic order. Yeah, I like that. I like that a lot, actually. I am impressed. For n larger than 3, there is no intrinsic linear cyclic order on the vertices that depend only on the normal. The normal orients the n-1 dimensional intersection polytope, but does not include a one-dimensional sequence of its vertices. That said, you can still produce a deterministic total order if you're willing to fix an in-plane frame in a canonical way, derived from the normal and the coordinate axis. I am willing, but yeah, if it has any meaning is then a big question. Below is a clean way to do it, plus the efficient edge vertex extraction you outlined. Geometric recap. Let the hypercube be 0n. Let the hyperplane be x element of Rn. And n dot x equals d. That's the same as I already used. With n is unequal 0. I chose an oriented normal. The intersection P is H yeah, okay. H intersected with a hypercube, I guess, but oh, it just takes the solid hypercube. Then you get a solid convex n-1 dimensions. Polytope, possibly empty or lower dimensional in degenerate cases where the plane skims face/edge. Vertices of P are exactly points I also can't say anymore that the word explaining is arrogant. It's definitely doing that. Vertices of P are exactly points where H intersects an edge of the hypercube, whose endpoints lie on opposite sides. or one endpoint lies on edge. For an edge with what did I what? I don't get the opposite sides here. Well, I use adjacent sides, but yeah, I don't know. So basically, that is the definition of an edge. Oh, opposite side of the hyperplane. Yeah. No, never mind. Yeah, of course. Okay, so or one endpoint lies on edge, but I don't want to consider that. Yeah, so you get this convex polytope, and then all the vertices of that, aka corners, are exactly those intersections that we are looking for. Still have this picture here. So yeah, here. So this is our convex polytope. Convex meaning that it doesn't have a dent. It's not like this. So from if this was a room, then from any point in the room you can see all walls at all times, and all the corners are exactly the intersections with the edges of the cube. Yep, totally true. Where's my mouse? Which endpoints lie on opposite sides, or blah, blah. For an edge with endpoints U and V, element of well, the binary number SU. What is S? Oh, those are the endpoints, I guess. No, it's not. Gee, maybe the definition here. SU is N dot U minus D. Oh yeah, this is the distance. So I think S stands for side. If these things are positive, then it's on one side of the hyperplane, and if it's negative, it's on the other side. So one must be on one side and the other must be on the other side. Therefore, they must be less than 0. And both not 0. So let's leave out the equal sign. The intersection point is okay. Efficiently enumerate each edge exactly once by toggling one bit from 0 to 1 for each corner index I from 0 to 2 to the power n, and each dimension k with bit k of I equal to 0. This seems nonsense. This is just exclusive OR, so it just toggles 1 bit. Yeah, maybe this determines an ordering. And say the bit here is 0 and the bit here is 1 on this side. And not the other way around. So that gets rid of the duplicates. Yeah, okay. That yields exactly, I guess it's still the number of edges of n is n times 2 to the power n minus 1. Okay, yeah, it didn't work out my recurrence, but apparently this is the formula. What ordering is natural? N is 2. Intersection of line and square. I want this segment with 2 endpoints. The oriented line gives a linear order along the line. Flipping n reverses it. 3. Tight orientation gives an rotational right-hand rule that yields a cyclic order of vertices around the polygon. The reversing n flips clockwise to counterclockwise. Any linear order you produce must break the cycle at an arbitrary starting vertex. I'm not super convinced that it really follows a cyclic order around our polytope. I mean, of course you have an ordering, but why would it go from here to there, and then there, and then there, and then there? Why not like all over the place? The ordering happens, of course, in the direction. Sorry, ordering happens. If this is x, yeah. So there is an ordering of my edges. In fact, I know that ordering still. This edge first, and then that edge, and then I guess then the third edge. And then this one, this one, this one. But that one, we counted that one double, so I wanted to go to 0, 1 first. Well, there's a certain ordering. Let's say, I don't know, this, 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 and then the thing at the back. Let's say that this point here is, I mean, then for the edges, you can take the smallest corner first and then enumerate over all connected edges. And this one was before that one and that one. So this edge is then the first edge. And then the next intersection point would be this one, because it has this edge in it. And the next intersection point for a cyclic order to exist, then for some reason must be that point. But why? You do, if you go from one intersection point to the next, then you follow a straight line over a face. So for example, from here we go diagonally over this face here, and then the back face, and then the bottom face. And here too, there's just 1, 2, 3, 4 faces involved every time. The back face, the right face, front face, left face. Going diagonally over a face, you can have two possibilities, I think. Either you cut off a corner. I think it's the corner behind here that is the most significance. And here we got two corners. Yeah, if you have a straight line, then you either go to well, in the three-dimensional case anyway, you go to an adjacent edge. So this edge and then that edge, they are connected here. Or you skip one, you go to the opposite side of the edge. And if you go to an adjacent edge, then those two edges have a common corner. For example, in this case, if you go from here to there, this corner of the cube behind the triangle is the common corner of this edge and this edge. Therefore, going from here to there swaps this edge with that edge. So only one corner is changed. And if now this corner behind the triangle would be lower in value, then it would be first in the pair that makes up edges, which means that this edge would be ordered before that edge, for example. But we can of course cut this cube any way we want, and it might also be that this corner is not less than that corner, that this corner is less. Then this one is up front. And maybe, yeah, hope. Yeah, I don't know. I'm just not seeing it or not convinced that it is cyclic. But maybe this is actually more talking about what the title says. So more like let's go of the predefined ordering that I was defining, and ask ourselves what is a natural order. Then you can just state that the natural order is the cyclic order of vertices around the polygon. You see, that's what it means with linear order. So maybe it says this doesn't work with your ordering, but cyclic order would be at least geometrically meaningful. So maybe you need a different definition. Okay, if you have more than 3 dimensions, the hyperplane is 1 dimension less. Orientation of n-1 manifold polytype is meaningful. But there is no canonical one-dimensional or cycling listing of all vertices from the orientation alone. You can, however, derive a deterministic total order once you choose an oriented orthogonal normal base of the hyperplane, which the normal determines only up to an in-plane rotation. So the geometric meaning of your normal depend order, meaningful cyclic order only for n is 3, and a larger than 3 you need extra structure as an in-plane frame to turn orientation into a total order. Is this the last paragraph? No. Practical canonical order, all n. You can define a deterministic order that depends smoothly on n. Flips when n flips. N is the normal, I guess. Is invariant to uniform scaling of coordinates. So cubes versus hyperblock via affine scaling won't matter. Collect unique intersection vertices. Step A, collect unique intersection vertices. Use the edge test above, deduplicate via hashing with a tolerance if you expect nearby coplanar degeneracy. Build an oriented basis of the hyperplane. Yeah, it's reached the PhD level. I think they trained it on a lot of mathematics papers. I'm having trouble reading this. How about to take a break? I'm going to take a break and eat and watch a movie. Yeah, but it looks like it's already exactly what I have, except for this line. And I didn't get it, so I would be very surprised if this is indeed giving a cyclic. If this is cyclic over the polytope corners. I'm first going to copy this, or copy it. I mean, okay, so we run over all corners and then all dimensions. And then only if the bit is not set, we continue and then we toggle it. What I had was this. I just reset the bit. So if the bit is not set, nothing happens. So I'm doing it. Well, actually, the bit is set in CI2. Haha. No, not true. CI. So this is the opposite then. Maybe I did this to be less cyclic, or sorry, less branches. We have to do this if anyway. So instead of a continue, I use the fact that if CI and CI2 are the same. So what I can also do is set a bit, and so I can do it like that. But yeah, that doesn't do anything, I think. I mean, it's not a significant difference. But let's show this to the AI. Fuck, stupid mouse. Copy. I'm gonna pretend I already had that minor change as well. So what I already had is that seems to be the same as your code. It gives the distance to the hyperplane of that corner. obviously. Okay, so by only setting the bit in CI2, in CI, setting the bit in CI, the side can only be different if the bit in CI was 0. So if you agree that this is the same, then I can just keep my code. What I do not understand is why this leads to a cyclic ordering. Of the corners of the polytope. Can you explain how that is guaranteed? By running over all edges like this. Hmm? Well, it's going to be deterministic, but I guess it only adds that to... No, don't have to add that. It is already saying 3D. You need a second step. So the code that the AI gave here is also not cyclic. So I'm completely right to say I don't understand why this would be cyclic, and I'm pretty sure it implied that. Nah. But okay. How to get a cyclic order in 3D. Compute the unique intersection points. Your current code optionally dedub with an epsilon. Build an oriented 2D base of the plane from the normal in. Pick a coordinate axis. I think it just wants to sort it afterwards, right? Yeah, sort. Yeah, that's kind of lame. But okay, so apparently it is indeed just arbitrary. And the only way to sort it is by doing a lot more work afterwards, which sucks because I wanted to avoid that. At least according to this AI, I can still think about it myself. Of course, I don't have the time for that, but it's super interesting. Maybe I will muse about it a bit longer. For now, I think I'm going to make dinner and watch a movie and stuff. Or I can just copy this code and then call it a day, of course. That also would work, probably. Yeah, I have to say that this is definitely worth 20 euros or dollars. What is it? I think I paid 23 euros a month. It's not all nonsense anymore. It's sometimes pretty impressive, actually. Compare that to the 2 generations ago, where I didn't even understand the difference between a plus and a minus sign. So minus 1 and 1 was the same thing in the eyes of the AI, because it's just a minus character. Just a hype in between two words. Okay, I'll be back later.